Hi there, this video is going to give you an overview of quantum numbers and atomic orbitals. Here is a summary of all of the quantum numbers, or I should say the first three quantum numbers that you will be interested in working with in your chemistry careers. We start with the first quantum number, which we designate as n. That is the principal quantum number, and that tells us about the size or the energy of the orbital that our electron is occupying. This is the same n that we've encountered when we talked about the Bohr model and calculating the energies of the Bohr orbits and energy levels for the hydrogen atom previously. So same n represents exactly the same thing that we've been talking about up until now. Our second quantum number that we're interested in is called the angular momentum quantum number. Okay, and that's given by the letter L, lowercase l. That quantum number tells us about the shape of our orbital. Okay, it's going to give us some information about whether it's spherical, does it have kind of a lobe shape or a four-leaf clover shape. Okay, that information comes from our quantum number L. Okay, so L can take on essentially any integer value from 0 to n minus 1. Okay, so we can see here that L depends on the value that we have already selected for n for a given orbital. Okay, so remember we've already seen what the values of n can be. They can be any positive integer starting at 1. Okay, so the value of L depends on what we've already selected for our n. Okay. And our third quantum number we're going to talk about right now is the magnetic quantum number. That is given by the notation of m sub l, okay, little m sub l. And this quantum number tells us about the orientation of our orbital in space. Okay, that tells us if we're oriented on any particular axis, like our x, y, or z axis. Okay, it just tells us how that orbital is oriented in space. Our m sub l is also dependent on the quantum number that comes before it. Okay, so we can see that m sub l depends on the value that we have determined for L. Okay, so we see a little bit of a pattern here where m sub l depends on our L, which depends on our n. Okay, so they are very much intertwined with each other. Okay, so now looking at this image here, this just gives us a little visual about how our three quantum numbers that we're talking about right now are related to one another. Okay, so we always start with n down here. So n pretty much dictates the options that you're going to have for your quantum numbers, for your other quantum numbers. So if n equals 1, we see that the only option for L in that case is going to be n minus 1, which is 0. Okay, so we only get one option there for L, okay, based on our limits. If L is equal to 0, again, that only gives us, based on our limits for m sub L, that only gives us the one option of 0 for m sub L. Okay, so a nice simple track for the n equals 1 situation. For n equals 2, so as we move up in energy, so as we go higher and higher in our n value, we're going higher and higher in energy for our orbitals. Okay, so for our next highest energy level or shell, if you would like to call it, but it's also known as a shell as well as energy level. Okay, so for n equals 2, we have now two options for our angular momentum quantum number for the L. Okay, so if n equals 2, we can have 0 or 1, right? So remember, 1 ends up being the limit of n minus 1 that we have for this example. Okay, so if we take this route where our L takes on the 0 value, the 0 option, again, we're limited to just the one value for m sub L in that case, where we get 0. Okay, so just like we had over here. If we take the option of L equals 1, in this case, we can have multiple options for m sub L. So remember, m sub L ranges from minus L, 0 to plus L. So if our L equals 1, that means we get values of -1, 0, and +1. Okay, and that's why we have these three different tracks coming off of our L equals 1 option. All right, so hopefully you're starting to see the pattern here. So again, as we go higher and higher in energy, so now moving up to n equals 3, you see we get lots more options for our electron orbital quantum numbers. Okay, lots more ways for our electrons to be essentially occupying orbitals in our atom. Okay, so for n equals 3, again, we have a limit to our options for L that stop at n minus 1, so we can go up to L equals 2 in this case, so we get options of 0, 1, and 2 for our angular momentum quantum number. And each one of those is going to have a set of m sub l's that go along with it. So again, our L equals 0 just gives us the one option of m sub l equals 0. Our L equals 1, just like our previous example, gives us the options of -1, 0, and +1. Okay, now we have an additional option of L equals 2. Okay, so again, m sub l can range from -L through 0 to +L, so we'll get -2, -1, 0, +1, and +2 options for m sub l. Okay, and we can keep going to n equals 4 or 5, all the way up to n equals infinity if we really wanted to. But you can imagine that you start to get quite a variety of options for what we would call atomic addresses for your electrons in an atom. Okay, the only other quantum number left to consider after these three is our spin quantum number. So just a reminder, remember we also have our m sub s, that's our spin quantum number. Okay, so that can take on values of +1/2 and -1/2. Okay, so for each one of these options that we end up here, at the end of our tracks, each one of those would have another two options for your electron assignment. So this set of quantum numbers of 1, 0, 0 could have a spin of +1/2 or -1/2 associated with it. So also here, +1/2, -1/2, +1/2, -1/2, +1/2, -1/2, +1/2, -1/2. Okay, so each track gets another two options for your electron. Okay, so for each orbital that you end up with, you can have a total of, so essentially all of these options that we terminate with here represent an individual orbital. Okay, so this would be an s orbital. Okay, whenever you have an L equals 0 option, you have an s orbital. Here's another s orbital. We have L equals 1, that corresponds to a p orbital. So we have three p orbitals, right, that just differ in their orientation in space. Okay, so again, an s orbital, p orbitals. Here, our L equals 2, that corresponds to our d orbitals. Okay, so we have 5 d orbitals. Okay, each one of those orbitals can have two options for your spin, +1/2, -1/2. Okay, so you can put up to 2 electrons in each one of these individual orbitals. Okay, so we get 2 electrons for every s orbital, 6 electrons for every set of p orbitals. Okay, so we have 3 of them, 2 electrons in each, and then we can have up to 10 electrons in our d orbitals, right? So 2 in each of these 5 d orbitals. Okay, so another word that you'll see used to describe these would be subshells. Okay, so when you're looking at your different L values, so these would be for the same n different L values. Okay, so every sp d or f orbital that falls within the same energy level, okay, we call those subshells. Okay, so now that we are feeling familiar with the individual quantum numbers that we use to describe electrons in our atoms, we can use those quantum numbers, as we mentioned, to tell us something about the atomic orbitals. So remember, atomic orbitals are just mathematical functions. Specifically, we call them wave functions, okay, and we give them that symbol psi. So each psi essentially represents an atomic orbital that is dependent on those first three quantum numbers that we just talked about. So the n, l, and m sub l. Those are all going to dictate what kind of wave function, what kind of mathematical function describes where your electron is located in your atom. Okay, if you want to think about psi, your wave function, in a physical way, if you square that wave function, okay, that gives you information about the probability of finding an electron in a given space. Okay, so it's important that to remember that it's the square of your wave function that gives you that physical picture of the probability of finding your electron in a certain region of your atom. Okay, the wave function on its own doesn't really give you any physical information. It's really just kind of a mathematical description of your electron. Okay, so here is an image from Wikipedia that has a nice summary of all the different kinds of angular parts of your wave function. Okay, so just kind of pointing out there that these are only the angular parts. There's also radial parts that make up your full wave function. Okay, it's actually impossible to plot both of those together, so we tend to focus on pictures that represent the angular parts of our wave function. Okay, so those are our s, p, d, and f orbitals that we've been talking about. Okay, so you'll notice that all of your s orbitals, so when L equals 0, remember that's an s orbital. These are kind of tiny. I'll try to zoom in here, but you can see that they're all spherical shape. These are just cut in half down here to show you that as you get to higher energy levels, you get slightly more complicated orbitals. Okay, we start to have things called nodes that pop up, which are little regions where you don't find any electron density. Okay, don't worry about that too much right now. You'll get to spend some more time with that when you get to some of your other chemistry classes. For now, we're just interested in getting acquainted with the relative shapes of these different orbitals. Okay, so s orbitals are spherical. If we look at our p orbitals, remember those are for the L equals 1 situation. Those correspond to p orbitals. Okay, if we look at our lowest energy p orbitals, these have that lobe shape, okay, where we have a positive lobe and a negative lobe. That's what those colors indicate. Again, don't worry too much about that, but just look at the overall shape. Okay, so we have one oriented on the z-axis, one on the x-axis, and one on the y-axis. That's where they get their names, right? Each one of those corresponds to a different m sub l value. Okay, that's where we get our 3p orbitals. Okay, x, y, and z. As we go to higher energies down the row, okay, you can see that they get really funky looking. Okay, so just as you go to higher energies, you'll just see that your orbitals get more and more complicated. Again, we'll save those adventures for some more advanced chemistry classes. So if you're interested in seeing why these orbitals look the way they do, go ahead and take some inorganic chemistry down the road. Okay, so moving on to our d orbitals. Here L equals 2, right? So remember L equals 2 corresponds to our d orbitals. We have 5 of them. Okay, based on our different m sub l's that are possible. So we've got m sub l equals 0, plus or minus 1, and plus or minus 2. So we have a total of 5 d orbitals that we can have. Again, our lowest energy d orbitals are the ones that are going to start to look most familiar to you, that we're going to focus on. They just differ in their orientation in space. They tend to have that kind of four-leaf clover shape to them. Again, you'll see that they just differ in how they are positioned. Okay, and then there's this one wonky one, our dz squared orbital that takes on a special shape. Okay, we won't do much with f orbitals in this class, but remember f orbitals, or at least in terms of looking at the pictures of the orbitals, f orbitals correspond to our L equals 3 Okay, so given all the m sub L values that are possible, you see that you get a total of 7 f orbitals that we get to draw fun pictures for. Okay, again, these are going to come into play when you get into some more advanced chemistry classes like inorganic chemistry. We won't dive too much into this semester, but just so you have an idea of what those start to look like. Okay, so you can get some really fun pictures with these orbitals as you go to the higher energy. All right, so just taking an extra minute to look a little bit more closely at the p orbitals. Okay, we're going to see these pictures come up again as we start to talk about bonding in our atoms. So we want to make sure that we feel comfortable with what these pictures represent. Okay, so these are our three 2p orbitals. Okay, so remember 2p, n equals 2 is the first energy level where we start to see p orbitals coming into play. So these are going to be your lowest energy p orbitals that you'll work with. Again, we've got 3 of them based on our m sub L's, okay, that are possible. Remember for L equals 0, right? So this corresponds to L equals 0 is a p orbital. So that means, oops, I hope you just caught me right there. It's not L equals 0. I'm going to leave this in there so you can see that I also make silly mistakes sometimes. Okay, hopefully you're screaming at me through the computer that L equals 1. L equals 1 for a p orbital. Okay. Whew, that was close. All right, so L equals 1 for a p orbital. That means that we can have m sub L options for -1, 0, and +1. Okay, so basically it's just convention that the z-axis gets the 0 label. Don't worry too much about it right now, but just know that each one of these represents one of our m sub L values. Okay? As far as you're concerned, you can just kind of arbitrarily assign them right now. We'll get to the details of those when you make it to quantum chemistry down the road. Okay, so again, just highlighting the idea that each one of these different m sub L values represents a different orientation in space. Okay, so for the px labeled orbital, that is just one that is oriented directly on that x-axis. Okay, so you can see that this orbital is aligned directly on our x-axis. Our py orbital, likewise, is aligned directly on the y-axis, and our pz orbital is aligned directly on that z-axis. So if you were just given these pictures, like I have here, okay, you should be able to identify this as a px orbital, a py orbital, and a pz orbital, okay, just by recognizing which axis that orbital is aligned on. Okay, that's how they get their labels. This picture right here is just a composite view. Okay, this is all 3 of these orbitals just overlaid on one another. Okay, that's what it actually kind of looks like in your atom, because all 3 of them obviously are existing at the same time. Okay, so again, this sort of picture will come into play more when we talk about bonding. Okay, likewise, let's take a minute to look closely at our 5 3D orbitals. Again, just kind of giving you a sense of how they are named, how they're labeled. Okay, so we have 5 of these d orbitals. These are the lowest energy d orbitals. So remember, n equals 3 is the first time you're going to see the presence of any d orbitals. So remember, for d, this corresponds to L equals 2. Okay, so if L equals 2, that means we have m sub L options for -2, -1, 0, +1, and +2. Okay, again, this is just our same quantum number rules that we're applying here. Okay, so we have 5 options for orientations of our d orbitals according to m sub L. Okay, so that's where we get our 5 pictures of our d orbitals, okay, or 5 orientations. So this first one, let's see how it gets the dxy label. Okay, so if we look at this picture, we can see that we have a lobe that is oriented directly between our x and y axes. Okay, so here's our x-axis, here's our y-axis, and our lobe is right in between there. Okay, so that's why this one gets the XY label. Okay, if we go over here to the XZ, we notice a similar kind of situation. Okay, we have a lobe that is directly oriented between our X and our Z axis. Okay, moving over here to the YZ, hopefully you can start to see how this is coming together here with the labeling. Might be a little bit hard to see this one, but this lobe right here, okay, if you can picture this in space, is oriented directly between the Z and the Y axes. Okay, so that's why we get the YZ label. This one's a little bit more fun. It has an x squared minus y squared label. Okay, this is telling us that we have lobes oriented directly on the x-axis and directly on the y-axis. Did I say y-axis twice? Directly on the x-axis and directly on the y-axis. Okay, so that's where we get the x squared and y squared. Right, and then this one should be easy to remember because this is the wonky one that doesn't look like any of the other four-leaf clover options. Okay, so this looks like a p orbital with a little inner tube around it. Okay, that's your dz squared, which you can remember because everything's lined up on that z-axis. Okay, so that's how we get our different labels there. They seem a little bit kind of strange, but hopefully that gives you a sense of how those labels make sense. Okay, in our last little bit here, let's take a few minutes to do some practice problems with our quantum numbers. So why don't you take a minute, pause the video, see if you can tackle this question asking what are the possible sets of the four quantum numbers for an electron and an atom when n equals 2. Okay, so here your only piece of information that you have to go on is that you have n equals 2. So take a minute and see if you can account for all the possible quantum numbers that you can have for n equals 2. There's going to be a few of them. Okay, so take a minute, see how you do with that, and then come back to the video and check your work. Okay, hopefully you have devised an assortment of possible quantum numbers for the n equals 2 option. So let's walk through what you hopefully ended up with. So we know that n equals 2, so the only options we're ever going to have are n equals 2 here for this example. Okay, I found it to be easier to account for everything by making a table for all of my quantum numbers. Okay, so I have a column for n, l, m sub l, and m sub s. Okay, so again, all of our n's we know are going to be 2, so that column's easy to fill out. Okay, now we have to account for the possible options for L, right? So we know that n equals 2, we know that means L can be either 0 or 1, okay, because we can go up to n minus 1, which in this case is going to be 2 minus 1, which is 1. So we get the two options for L. Okay, so we can put these options in for our L. So we're going to have zeros or ones in this column, okay? And then we need to think about the possible m sub l's that are associated with each of those values for L. Okay, so remember for L equals 0, the only possible value for m sub l is 0. Okay, if you go back to the train tracks, okay, remind yourself of that. Okay. Now for the L equals 1 options, we have a few options for m sub l. Okay, so remember when L equals 1, m sub l can either be +1, 0, or -1. Okay, and we get two options for each of those, okay, based on our spins. Okay, so you'll see that for every m sub l option we have, we get a +1/2, -1/2. Okay, so for m sub l plus ones, we get +1/2, -1/2. For m sub l of the zeros, we get +1/2, -1/2. And again, for the negative ones, +1/2, -1/2. Okay, so we have one set of quantum numbers for the L equals 0 situation, right? We get two options there. These are going to be our s orbitals, right? So L equals 0 is an s orbital, and we can have one electron spin up and one electron spin down. When we go to our p orbitals, okay, remember we have 3 p orbitals, okay? One p orbital with m sub l +1, okay? that orbital can hold a spin up and a spin down electron. Okay, so we get two options for that orbital. We have another p orbital with a different orientation, okay, different orientation of m sub l equals 0. That orbital can have electron spin up or spin down. Okay, so we get another two options for that. And our third p orbital for m sub l minus 1, again, that orbital gets options for spin up and spin down. Okay, so we get another two options there. So hopefully you might have approached this in a different way, and that's fine, as long as you end up with all of the same sets of quantum numbers, but you should end up with 1, 2, 3, 4, 5, 6, 7, 8. You should have a total of 8 possible sets of quantum numbers for this particular example. Okay, again, just remembering your rules for quantum numbers and making sure you account for all of the possible options. Okay. All right, in this practice question, we're going to see if we can remember how to identify what quantum numbers are allowed and what are not allowed. Okay, so see if you can take a minute, pause the video, take a minute to see if you can identify which, if any, of these sets of quantum numbers that I've listed here are not allowed. Again, go back to your rules. Okay, remember that each subsequent quantum number depends on the one before it. Okay, so apply your rules and see if you can find out if any of these are not allowed. Okay, hopefully you took a minute to go through that and identify whether any of these were not allowed. So let's just go through these step by step. So remember the ordering here. These represent your N, your L, your M sub L, and your M sub S quantum numbers. That's the order that we're representing those. Okay, it's always going to be the order. So be very okay, so we have our first set of 4, 2, 2 plus 1/2. Okay, so if n equals 4, okay, we ask ourselves, is there anything preventing our L from being 2? Okay, so if we have n equals 4, we should have options for L of 0, 1, 2, or 3. Okay, remember, go up to n minus 1. So an L of 2 is okay, right? So nothing bad so far. And then we know that m sub L can range from minus L through plus L, all of those integers. Okay, so m sub L, if our L is 2, should be able to take on values of minus 2, minus 1, 0, plus 1, or plus 2. Okay, so 2 is okay there. And then m sub S, remember, it can have a value of either plus 1/2 or minus 1/2. So here we have a plus 1/2. This one looks a-okay to me. Okay, so I don't see anything wrong with those 4 quantum numbers. All right, let's look at the next one. So once again, we have n equals 4. That's always allowed. If we look at our L, possible values for L for n equals 4 are going to be, again, 0, 1, 2, or 3. So that 1 is just fine. Our possible values for m sub L for an L equals 1 are going to be minus 1, 0, plus 1. Okay, so that 0 is okay. And we have a minus 1/2 for our spin, which is okay. So again, I'm going to give a seal of approval to that set of quantum numbers. I don't see anything wrong with those. Let's look at our last one. Again, n equals 4. L equals 2. By now, hopefully you can recognize that as an acceptable number for corresponding to an n equals 4. Okay, we get options of 0, 1, 2, or 3. So 2 is okay. M sub L options for an L equals 2 should be minus 2, minus 1, 0, plus 1, or plus 2. So right now I'm seeing a bad news bears on that 3. Okay, so 3 is not going to be allowed as an M sub L value for an L equals 2. Okay, so here, remember, your M sub L can only be minus 2, minus 1, 0, plus 1, or plus 2 for L equals 2. Okay, there's nothing wrong with that spin number. Okay, we can have a plus 1/2, but this m sub l value violates our quantum number rules, so that one is not allowed. Okay, hopefully that helps you to feel more comfortable working with the quantum numbers. Keep practicing, and thank you.